Welcome. This is Dr. Thom's crash course in the course formerly known as Thermo I. Well, the starting place for almost any thermo-type problem is conservation of mass, which you learned back in ES201 ConApps. So to apply conservation of mass, you always start with the system. Very, very important. And be sure to draw all your transport terms on the system itself. That's very important. Okay? So once you have your system identified, there's two basic different ways you can apply conservation of mass. The first one is to a closed system, in which case you get something quite trivial. For a closed system, there are no mass flow rate terms, so dmdt of the system is 0. Or, more succinctly put, the mass of the system is constant. We often don't use conservation of mass for a closed system, but we're going to find it in this course. Sometimes it turns out to be very helpful. If we have, on the other hand, an open system that's operating at steady state, that means that dmdt is 0. That is, nothing in the system is changing with time, and that includes mass. You'll notice something very curious about these two forms of conservation of mass. Both of them say dmdt is equal to 0, but for completely different reasons. For a closed system, dmdt is 0 because there's no way to get mass in or out of the system. Therefore, mass stays constant. In a steady state system, however, dmdt is 0 because nothing's changing with time. There could be flows in and out. It's just that all the flows in balance all the flows out. The order in which you cross out terms is important. Moving right along. Next big stop when we're looking at thermodynamic problems is to apply the conservation of energy. As with conservation of mass, it's very important to identify your system clearly. When you're dealing with conservation of energy, transport terms include heat transfer terms, Q, mass flow rates, which bring energy in and out of the system with them, and also power terms, work per unit time. Here's what I call the big, long, nasty equation. This is conservation of energy applied to a general open system. There are two flavors of terms on the right-hand side. The ones with all the m dot terms. Those occur at flow boundaries. That's where you have mass flow rate crossing your boundary. Q dot and W dot both occur at what we call non-flow boundaries. These are where you have no mass flow rate crossing your system at all. Okay, so one of the big skills that you have to have under your belt when you're applying conservation of energy is to simplify the big, long, nasty equation appropriately for all sorts of different assumptions. Here's a big one that we make a lot in the world of thermodynamics. That is, that there's no kinetic or potential energy terms. Give yourself a second to write down what you think conservation of energy looks like with no kinetic or potential energy terms anywhere. Okay, well, I'm hoping what you came up with was something that looks like that. Notice that there's no v squared or gz terms in the mass flow rate terms. That's because those are kinetic and potential energies. Also notice that the dEdt term on the left-hand side became a U term. Only internal energy is important. So kinetic and potential energy of this system was also ignored. And please don't make this terrible, fatal mistake, which we see quite a bit. Don't confuse internal energy with specific internal energy. They have different dimensions, different units. In general, you can get big U by multiplying little u by mass. But if you use one when you need the other, you can have a fatal mistake that you'll never recover from. So please be sure not to make that mistake. The general form of conservation energy requires internal energy, big U, not specific internal energy. Okay, so let's have our hand at applying this conservation of energy to a number of other types of systems. First off, let's apply it to a general closed system. If we have a general closed system, what goes away? That's right, all the mass flow rate terms go away, and you end up with just dEdt is Q dot in minus W dot out. You'll notice that I'm using W dot out and a minus sign here, where in the general equation itself, we've got plus W dot in. They say exactly the same thing. In this course, we're going to start using the opposite sign convention that we learned in ES201. That is, that work into our system is positive. We're going to assume that work or power out of our system is positive instead. Therefore, you need this negative sign right there. You should be comfortable doing either one. One way to not mess that up is to always write subscripts on your Q and W terms, and that'll remind you whether you need a plus or minus sign out in front. Okay, so if you're going to apply this equation to a steady-state open system instead, what should you get? Hopefully you guessed that. dE dt goes away. That means that the energy of the system remains constant. Everything looks the same now as it always will. That's the definition of steady state. So if you're still having a little trouble trying to understand what steady state means, now's a good time to really review that process. Steady state means nothing in my system changes with time. If you took a picture of it now and you took a picture of it 1,000 years from now and you looked at those two pictures, you wouldn't be able to tell that anything was different at all. That's what we mean by steady state. Nothing is changing with time. Time derivatives go away. That includes mass, energy, momentum, anything that you look at. Okay, so let's reduce a little bit more. If I have a closed system and it's over a finite period of time, how do I reduce this equation even further? Okay, hopefully you came up with this. The change in energy between some time 1 and time 2 is equal to the heat transfer that came in minus the work that left over that period of time 1 to 2. Notice that the dots are gone. When you integrate a dotted term with respect to time, the dots go away. When you integrate dE dt by dt, then it just turns into delta E. So this, in my experience, has been one place where students have a lot of difficulty, is going from the general form of conservation energy to this finite time. When you think about the result of the finite time conservation energy, however, it's really pretty simple. It basically says that if energy comes in via heat transfer and energy leaves minus work, then those two things have to end up being a change of energy of the system, because there's no other way to get energy in and out of a closed system with no mass flow rates. It's perfectly okay with me if you want to start with this form of conservation of energy when you recognize that it's appropriate. That is, that you have a closed system over a finite period of time. And last but not least, let's look at a steady state open system, which also has no kinetic and potential energies. That will give you, you guessed it, 0 is equal to Q dot in minus W dot out, plus the summation of M dots times their enthalpies coming in, minus M dot times enthalpies leaving. All of these forms can be found using the most general form with the appropriate assumptions. So that's the skill I think is really important, is that you can start with this and get any form of conservation energy that you need given the appropriate assumptions. Okay, so that's a big part of doing thermodynamics problems, looking at conservation of energy and manipulating it appropriately for your given system. Another big piece is how to deal with properties. How do I get H's? How do I get little U's? How do I find those kind of things? And the answer to that is, well, it depends. It depends on what you're modeling your stuff as. If you're modeling your stuff as real stuff, where you have to rely on experimental measurements of those properties, then you're going to look stuff up in tables. We use this type of model for water, for different refrigerants, and basically any time we've got stuff that is in any danger of changing phase. It's a liquid, it's a gas, it's a mixture between the two, or that phase change could happen if I change the pressure and temperature appropriately. So let's first off look at how I calculate properties when I have a real substance and the substance is superheated. That is, it's in the vapor phase. Basically, I just need two independent properties to fix the state of any intensive property. So in theory, if I know pressure and temperature, that's enough to find the specific internal energy, the specific entropy, the specific enthalpy, which I haven't written. But basically, any intensive property is fixed when I know two independent intensive properties. How do you find those? You'll look them up in tables. Okay. On the other hand, if I have a mixture of both a liquid and a gas, then pressure and temperature are not independent. So I wouldn't be able to look it up in a table just knowing P and T. For instance, when water boils at atmospheric pressure, you know the temperature is exactly 100 degrees Celsius. So pressure and temperature being 1 atmosphere and 100 degrees Celsius is not enough to fix the state of your substance. What do you do then? The answer is we need another property, and that property is quality. Quality being defined as the mass fraction of your mixture that is in the vapor or gas form. And in order to get your properties, for instance, U or little s, what you do is you use these handy little formulas. 1 minus x times UF plus x times UG, and a similar equation for S, a similar equation for H, a similar equation for V, etc. Let's think about what those equations mean. The 1 minus x represents the fraction of your mixture that's in the liquid form. If x is the fraction that's in the vapor form, then 1 minus x must be the fraction of stuff that's in the liquid form. So you take the fraction that's liquid, and you multiply it by the liquid property, S sub F being the, in this case, entropy of the saturated liquid in my mixture. And then the remaining term is pretty obvious. You've got the fraction of stuff that's gas, and you multiply it by the gas property itself. So any specific property, that is U, S, H, V, anything that's on a per unit mass basis for a mixture can be found in this way. The other option when you have these type of substances is that you have all liquid. And in that case, we almost always make this compressed liquid approximation. You can simply look up what your U or S or H is in your table given pressure and temperature, or pressure and specific volume, or specific entropy in U, or whatever two properties you have. But what you're going to find is that often those tables are very short. There are not many of them, and in some places they don't exist at all. So one easy thing to do, and this is pretty darn close, is you can approximate virtually any specific property as having exactly the specific liquid property at the same temperature. Please don't make the fatal mistake of assuming that the property is equal to the sub F property at the same pressure. It's only temperature. What this says is that these properties are very strong functions of temperature, but weak functions of pressure. There's one exception to this. If you're looking at specific enthalpy, you've got the sub F property, and then there's a small correction factor consisting of the specific volume of the saturated liquid times the difference in the actual pressure and the saturation pressure at the same temperature. It's often and usually small. There are cases, however, where it's the only piece that is left, and that's very common when we have pumps. We're going to see that later on in the course. So that's how we deal with compressed liquids. Okay, so there's another big category of substances. We just figured out, or just reminded ourselves, how to deal with properties of real stuff, which we use almost always when we have substances that are either changing phase or in any danger of changing phase. Ideal gases are another big classification. There are a bunch of different equations we use for ideal gases. Here's a big one. PV is equal to nRT, or P little v is equal to RT, or PV is equal to MRT, or PV is equal to NR universal times T. Many different forms of this equation, and you should be pretty good at using all of these forms. So you don't need any tables to calculate pressure, volume, density, those kind of things, if you know pressure, temperature, etc. But those equations don't tell us anything about U and H and V and S and all those things that show up all the time in thermodynamic situations. So for ideal gases, there's a unique thing about both U and H, which is not true for real substances in general. And that is both specific internal energy and specific enthalpy are functions of only temperature and nothing else. So you give me a temperature, I'll tell you what U and H both are if I have an ideal gas. Now, how do I go about doing that? Well, in general, a du is found by a c sub v times dt, and you have to integrate that. Those results are given to you in tables. So the bottom line here is if you have variable specific heats that change with temperature, you look up little u and you look up little h in tables. Just find the temperature and go down the table and find the corresponding u and h. Entropy changes, on the other hand, are a little bit weird because you need this strange combination of both tables and an equation. So you use this equation as super naught as a function of temperature, difference between that function for two different temperatures, and then there's this piece minus r times the natural log of P2 over P1. So you need both temperature and pressure to find specific entropy changes for ideal gases. This piece is a function of temperature only. That's from the tables. This piece is just something you plug in the equation. Okay, so notice that S super naught and S are not the same thing for an ideal gas unless you have zero pressure change. So do not forget this piece. You might recall that there are a bunch of equations that give you U and H and S changes for an ideal gas that don't involve looking things up in tables at all. What's that all about? Well, you can do that if you have this one very big assumption, and that is that your specific heats do not change with temperature and are one constant value. In that case, you can use all these equations. Delta U is C sub V delta T. Delta H is C sub P delta T. S2 minus S1 is C sub P log of T2 over T1 minus R log P2 over P1, etc. So you have to use absolute temperatures when you're using the entropy equations. And to use any of these equations, you have to have constant specific heats for your ideal gas. You cannot use these equations in one place in the previous tables in another place for the same problem, because now you're mixing your assumptions, which is very bad. How do you know whether to assume that C sub P or C sub V are constant? Experience is one way, but at your level, we'll usually tell you whether the assumption is okay or not. But big takeaway, don't mix the two sets of assumptions. Okay, so there's another model that we often use when we're looking at thermo type problems. It is the incompressible substance model. This applies to almost all liquids and solids, things that stay liquids and stay solids the entire time. In that case, we have a set of equations that look very similar to the ideal gas equations with constant specific heats. They're not identical, but they're very similar. So notice that you have this delta U is C delta T, delta H is a C delta T with a little V delta P term also. And here's the delta S that looks very similar to the delta S for ideal gases. So if you have a liquid or a solid and it never changes from liquid or solid to anything else, these equations are almost always perfectly fine. Okay, more stuff. So another big piece of thermodynamics is the accounting of entropy. This is the last equation that we're going to look at in this crash course in the course formerly known as Thermo I. In entropy accounting, as any accounting equation, you need to clearly identify your system, which is what we've done here. In a general open system, you've got mass flow rates too. But there's one very interesting thing about entropy accounting that's a little bit different than the identification of systems for other accounting principles, and that has to do with the temperature. You have these terms Q dot over T, and the T refers to the temperature of the boundary of the system, which may or may not be the temperature of the rest of the system. So entropy accounting is highly dependent on what kind of system you are looking at, and specifically what the temperature of the boundaries are of your system where heat transfer is occurring. So here's your general equation. ds dt is Q dot over T, m dot S is coming in minus m dot S is leaving plus S dot gen. You should go back and refamiliarize yourself with what those different terms mean. We're going to kind of do the rest of this crash course at an accelerated rate now. But some things that are different. Notice that there's a generation term for the first time. In fact, the only time in any of the conservation or accounting equations that you've seen before. S dot gen is equal to 0 and only equal to 0 when you have an internally reversible process. S dot gen is 0 then and no place else. If you don't have an internally reversible process, then entropy is not conserved. The book we're using for this course uses sigma for entropy generation and sigma dot for the rate of entropy generation. The way you learned it was probably a big S with a dot and a GEN subscript on it. So spend about the next 30 seconds or so taking your general accounting of entropy, and reducing it for a closed system, an open steady state system, and finally a closed system undergoing a finite time process. So write down how that equation reduces for those three different situations. Okay, I hope this is what you came up with. So for a closed system, we have no m dot terms. So ds dt of our system is q dots over temperature boundary plus s dot gen. If we have an open steady state system, there is no ds dt of our system, and our entropy coming in via heat transfer, and our entropy coming in and leaving via mass transfer, and our entropy generation inside the system all balance out to be zero. Do not confuse ds dt of the system with s dot gen. Beginner mistake. ds dt can be zero, bigger than zero, less than zero. No restrictions on what ds dt of your system is. S dot gen can be greater than or equal to zero. ds dt can be anything. Finally, closed system, finite time, our entropy generation turns into this. The entropy change of our system is equal to Q over temperature of the boundary plus the entropy that was generated during that finite time. As in conservation of energy for a finite time for a closed system, notice the dots go away when you integrate with time, and you have no ds dt, you have a delta S of your system. Also, like in conservation of energy, this is big S, not little s. Don't confuse your extensive and intensive properties. So we've already alluded to this several times already. The second law of thermodynamics says that S dot gen, or sigma dot, whatever you want to call it, is always greater than or equal to zero. It can never be less than zero. Only in an internally reversible process is it equal to zero. Okay, so we're almost done with our crash course of Thermo I. Everything you should have learned but may or may not have in all of 23 minutes. So here's some miscellaneous stuff that didn't really fit with everything else that we've talked about. First off, if you have a closed system, one way to calculate the work, if you have a boundary that's expanding or contracting, is by using the integral of minus p dv. So if you know pressure is a function of volume, you can integrate that booger and get the work into your system. With the opposite sign convention, which is what we're using in this course, the work out of a system undergoing expansion or contraction being calculated as the integral of p dv. In order to evaluate this integral, you do have to know how pressure changes with volume. This is volume, not specific volume. And also note that p dv is only equal to p delta v in the case of a constant pressure process. It's really tempting just to pull p out of the integral and go p delta v. It doesn't always work. You have to know pressure is a function of volume. We've also got our mass flow rate across surfaces, real or imaginary, by using the average velocity of a flow stream. Good old m dots equal to rho AV. And here's some miscellaneous relationships among properties that we're going to use from time to time. This is a really handy way to relate U, V, P, things that are easily measurable, to entropy, which is really hard to measure. So we call those the TDS equations. And that concludes our whirlwind tour of everything that you should have learned in Thermo I, but might be a little rusty on. The cool thing is you can go back and watch this as many times as you want to get these concepts back into your brain. So, welcome everybody to Thermo II. That concludes Dr. Thom's crash course, and the course formerly known as Thermo I.